What did we discuss? Dimensional analysis, scientific notation, metric system. Which ones do you have to have memorized? The metric prefixes. Kilo. Pretty much all of them except giga, tera.
Mega.
Okay. Yeah, I'll talk about the lab in just a second. So, starting off with the biggest, what's the biggest unit you should know? Tera. Right. Tera, then what? Let's go down. Giga, mega, kilo, hecto, and deca. We'll just skip those if you want, unless you already have them memorized. But we barely, in fact, we'll never use those in this class. Hecto and deca. Once in a while, you'll see deciliter in the homework, but other than that, we'll never use it. Okay, then what else? Okay, milli, centi, centi, milli, micro, nano, pico. And then there's actually one more smaller than pico. Do you know what the one more smaller than pico? Femto. Femto, the reason femto is important is because of lasers. They have lasers that can pulse light at femtoseconds, which is amazingly fast, if you think about it. That's not going to be. Femto's not going to be on the test, but femto's important in chemistry and physics. But let's continue on with our presentation. Was there anything else we talked about yesterday? Conversion factors, good. Anything else from yesterday?
The scientific notation.
Scientific notation, yeah. And?
How to do it in a calculator.
There's something else. There's something else we talked about yesterday. The SI. What was the SI? Or not SI. I didn't call it SI. SI units, yeah. Meter, that kind of thing. Significant figures we talked about. And so we'll be discussing significant figures. Continue. There's certain rules for significant figures. They're called rules. They aren't laws. But the question came up about significant figures, so this is a relevant question because you're going to see it when you go to Chem 1A, you'll see it in Chapter 1, Chem 1A, right at the start. In fact, not a bad idea to look at Chapter 1. This is from the Chem 1A textbook. This is a homework assignment I always give in Chem 1A in Chapter 1. What's the difference between rules and a law? These aren't the laws of significant figures. Yeah, there's going to be a lot more exceptions than rules. Whereas, something like propagation of errors could be like the law of propagation of errors. But sig figs have always been known. Even though this is 3 sig figs, this is 4 sig figs. You expect 4 sig figs to be more precise, but it's not always. And so, according to the rules on significant figures, the product of the measured quantity. Okay, so that's 3. This is 4. In propagation of errors, we don't look at the number of sig figs. We look at what it is very simple. The percentage error in each value is essentially what you're doing when you're doing all the mathematics for that. And so what we do here is our rules are just 3 sig figs, 4 sig figs, so our answer should have 3 sig figs to reflect uncertainty. But when we do this calculation and we round it to 3 sig figs, 100.7 would round to 101 to 3 sig figs, but that doesn't accurately reflect it. In fact, that overestimates the uncertainty in this particular one, because here, the uncertainty here is in the 1/10 of a meter here. This is what we call the uncertain digit, and that's going to have some spread to it. The uncertainty here is in that's a tenth, that's 100, so that's 1,000, the 1,000th of a meter. And so our final answer should reflect the uncertainty in the 10th place here, but according to the rules, it doesn't. And so we usually express this. It would be more appropriate to express this and break the rules It'd be more appropriate to express this to 4 sig figs than follow the rules and round it to 3 sig figs. And so rules, of course, are going to have more exceptions than laws. Laws you wouldn't expect many exceptions. So this is what we have to realize when we're dealing with significant figures. They're just rules. And it's hard to write a rule for every scenario you encounter, so you have to take them sometimes case by case, but for the most part, they work. And so tomorrow's lab, we're going to be doing a lot of measurements where we have to pay attention to the significant figures. We're going to count the significant figures, and we're going to do addition, subtraction, multiplication, division rules for significant figures. And so this is something to be aware of. Rules are different than laws, of course, and some people think of rules and laws as the same thing. We don't in science. We don't think of rules and laws. Okay. What else did we talk about yesterday? We talked about SI. I forgot how are things defined? Well, sometimes like a kilogram. How's a kilogram defined? Do you define it based on a gram? And then how is a gram defined? Sometimes you think about these things. Sometimes you ignore them because it doesn't really matter. Well, one of the suggestions was a gram is based on the water being that, but we'll just apply the rule. We'll just apply significant figure to water. In fact, I'm going to look. We're going to use this table tomorrow. This is there's different ways that we can visualize the density of water, and this is a table that confuses a lot of students in this particular lab. And so we're going to use a table like this. Actually, I have the one from our book. Let's take a look at this one because the one from our book is screwed up. This one's a lot easier to see than the one in our book. Okay, so if we look at the density of water at various temperatures, and so this is just showing the temperature and its density. So 4 degrees C, the density is 2. How many sig figs is this? Infinite? No, this is 7 sig figs. This is not infinite. It's not exact here at 4. Or maybe it is. It depends on how it's done. It could very well be. But if you look, the density of water changes. And so there are different things we could do. One thing is, well, if the density of water is changing, then maybe we could just memorize 1 at 4 degrees C, it's 1. Right? Or what we can do is we can, rather than say, what the density of water is, because there's no way I want to memorize all these, what would be safe? Would it be safe to say that the density of water is 1.000? Can we do 4 sig figs? The density of water is 1.000 grams per milliliter. That's, each milliliter weighs a gram. Well, that would work here, 1.00. That would work here. That would work here to 4 sig figs. But when we get to here, what would this be to 4 sig figs? So it turns out zeros before the decimal are not significant. And so that's what we call a placeholder. Some people don't even write the 0 there. They just write point, whatever. And so the number of sig figs here, we start counting after the decimal. Zeros preceding the decimal are insignificant. So 1, 2, 3, 4. That means we have to drop the 3. If we drop the 3, what does this round to 4 sig figs? No, it rounds to quadruple 9. 4 9s, 0.9999. So it's not 1.000. And so if we called the density of water 1.000 to 4 sig figs, it would work between 4 and 6 degrees C, roughly. Or 0, actually, 0. There's a blip. Below 4, the density actually decreases. This is a peak in the density of water. So what if we do 1.00? The density of water is 1.00, and that works over a wide temperature range. Is that valid? And so if we do the density of water to 3 sig figs, that would work. It works down to here. If we round that to 3 sig figs, 1.00. If we round this to 3 sig figs, would it work? No, what is this number rounded to 3 sig figs? 0.997. We drop to 0. So it fails at room temperature. So we can't call water 1.00 grams per milliliter at room temperature. Can we call water 1.0 grams per milliliter? Will that work over a wide temperature range, over all the temperature range? And so when we do that, well, when we start to get to higher and higher to 2 sig figs, it would fail at around 33. It's going to fail because this to 2 sig figs is going to be 0.99. This to 2 sig figs will be, well, we got to round it up. It's going to come out to 1.0. And so water will stay 1.0 grams per milliliter up to about 32. But most of our chemistry is done at what temperature? Most of our chemistry is done at room temperature. So, you know, we could say that water, rather than memorizing a number like this and it varies, it would be just much easier to say water is 1.0 grams per milliliter, you know, and that's it. We'll just leave it at that. And so this is the number people memorize. It's not exact, right? It's about 1.0 grams per milliliter when we use it, when we actually use the number. So that's only the 2 sig figs. Now, what if you need the number to more than 2 sig figs? If you need the number to more than 2 sig figs, we have to get it off the chart. Now, we're going to have to do that tomorrow. So I might as well talk about it now because save time tomorrow in lab. We're doing, what was the experiment number we're doing tomorrow? Well, one thing is you should skim over the lab or read the lab. You know, you should have some kind of mental idea of what we're doing. It's not so critical for intro chem because there's usually plenty of time. But when you get into higher level classes, there's no time. There's no time to waste. In fact, at UCLA, there was a 5-point penalty for each second you're over in lab. So 1 second over, that's because the next class comes in 5 minutes right after, you know, and everybody has to be cleared out at that time, and there's huge point penalties for overstaying your time in lab. And so if you aren't well prepared, that is, if you don't hit the ground running, you aren't going to finish lab. Everybody's used to that though. You get used to it quickly. All right, let's take a look at this here. So at 4 degrees C, maybe that is how it's defined, you know, at 4 degrees C, 1 gram. But, you know, how do you get 4 degrees C? You know, tell me at home, you want to cool something down to 4 degrees C. How are you going to do it? You put it in the refrigerator, but you put it in the refrigerator, it gets cold, right? You open the refrigerator, what happens? Warms up. How are you going to get a stable 4 degrees C? Well, what you have to do is you have to have a refrigerated laboratory. And you'll put on a jacket, go in there. You got to have enough power in the refrigeration system so that when you go in, you don't perturb the temperature because your body is warm. And the hot bodies and cold bodies, when they come into contact, they try to the cold, warm, the hot, cold, cool down. So they try to reach thermal equilibrium. It's very difficult to get, sometimes. And so I really doubt this is the way it was defined. There's got to be another way that the gram was defined, but we'll talk about that. Because people look for convenience. They don't want to build some very expensive laboratory at 4 degrees C. And so they look for convenience. Well, anyway, people look for convenience, so they don't want to, for example, here, what's going on with the density? A lot of people will say the density at 1 degrees is 927 grams per milliliter. 927 grams per milliliter. What was the most dense? What did I tell you the most dense elements are on the periodic table? Not cesium is very low density. Helium is very low density. One of the least dense, in fact, the least dense element on the periodic table is helium. I told you what the most dense ones were. It had to do with, remember I talked about it came from a meteorite? Iridium, right, iridium. Iridium, iridium is not that much more dense than gold. Do you know what the density of gold is? 19, a little under 20 grams per cubic milliliter. I told you the density of gold. Remember I said it's like 20 times heavier. If you had a gallon of water and it was gold, it would be like carrying 20 gallons of that water. You might think, okay, this is just memorization. This is just, not even worth spending any energy trying to understand. But if you don't learn some reference points, then you don't have an idea about scale, And so normally, you don't want to memorize every single reference point there is. Usually if you move to a town or something, you look for the highest mountain or the biggest tree, or you look for something to get your kind of bearing. Well, when you move into a new field, you need some kind of things, some kind of points memorized to give you a bearing, like the least dense, the most dense, these kinds of things, as far as it goes. The density of water, 1. Well, what's the density of wood? Like pine is like 0.4, 0.6 grams per milliliter. And so you need, most solids around 2, 2, 3, 4, 5, 6, 7, 8. The most dense solids would be like gold, 20. Gold is, and iridium's slightly more dense than that. Osmium and iridium is a couple of the most dense elements. Well, so a lot of people would have no clue. 927 they think is a perfectly acceptable number for the density of water. And so people will write down, well actually our water is not that cold. What is our water? Our water is, let me tell you what I've seen many times. Our water is around 22, 23. Our water is around 23 degrees, maybe 20. Okay, so, or 19. It's kind of cold out of the tap. So our water is 19. So I've seen this. Okay, this is 19.0 is 435, 19.1 is 415. I've seen this literally. I've seen people write down that the density of water is 415 grams per milliliter. Can you imagine that? 415 grams per milliliter is like a joke, but they were serious. They were serious because they had no clue what densities run about, because they have never memorized anything, This is why it's important, because, otherwise you look something up, there could be a typo, there could be some other mistake, you have to look something up on Google, Google's not always refereed, Wikipedia is better refereed, but some of the Yahoo answers and Google answers are ridiculous. They make you laugh because they're so far out of the, And so this is, so anyway, so something's going on here, because if gold is 20 and you're getting a density of water of 415, that's 20 times more dense than gold. How is that possible? How that's possible is this table's all wacky. I mean, it's screwed up, this table. You know why? Because they're kind of lazy, or they want to save. You know what? The first 3 digits don't change. So 0.99, just the last 3 digits change. So rather than writing it over and over again, they omit it. But you think, hey, it's tight, it's computer generated. Why not just write? I don't know. But in the old days, this is very common. And nowadays, it isn't so common. And so if the first 3 digits don't change, they leave it. And now here it changed. So we went up from 0.999 to 1.000. And then we go down. Actually, the density of water increases to a max of 4 and then starts to decrease again. And so this is 999, and then it stays 999. Now something else funny happens here. Maybe you could figure it out. And tell me what's going on here. What do you think's going on with this asterisk here? Okay, what's going on with the asterisk is this. Okay, the first 3 digits are 0.998, so 0.998. and it goes down. And so what's happening with the density? Density is decreasing, 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 decreasing until it hits 998, 000. And then it increases again to 998, 978? No.
Is it going to where 22's at with the .997?
Yes, right. Since they didn't want to write it in here, they should have wrote just .997 rather than .998, then we're still going down. Okay, so be aware of that. When you see an asterisk there, you have to refer to the other three digits here. Just look at the trend. Do you see the trend, the pattern? Now, the pattern is hard to see in tables like this sometimes. When you look at a table like this, that's a lot of numbers. You know, a lot of numbers, and pretty soon all those numbers come out as a blur. And so what scientists do is they do a process called data reduction. There are books written on data reduction. You know, how do you reduce all this jumble of numbers into things that are easier to visualize or easier to comprehend? And so, one easy way is just rather than put it in tabular form, we'll put it as a plot. And so, density of water plot. Let's show some images for a plot. And so here we can see this is the plot I showed yesterday. And so this is what's happening with the density of water. From 0 to 4, it increases to max and then drops down. In fact, when we think about the calorie is just defined between 4 to 5, or it might be 4.5 to 5.5. I have to check the definition. Because the amount of energy to heat 1 gram of water by 1 milliliter changes with temperature a little bit. And that little bit of change in temperature makes the math a little bit more complex. We need calculus to do the math properly for that. But we do it later. And so once we have this plot like this, then you know what? You know what the most compact way of representing this is? By a mathematical formula. And so what we do is we figure out the mathematical formula that defines this curve here. Once we do that, then we can call that the law of the density of water. The law of density of water is this mathematical equation. We can use that equation to predict the density at any temperature we want. Then once we have that, it's much easier because what you're going to have to do is read. Actually, we don't have to read between the lines. Our thermometer will only read to the nearest 10, so we're okay. We just read. But usually it's a little easier just to plug it into an equation and have it spit out the density. But the thing is, why? You know, the next question is, okay, so we have our observations, right? We found the trend, we found the pattern, we have the law. The law would be this mathematical equation, which we call what? What do we call a mathematical equation that's derived from observations?
Theory?
Not theory. A mathematical equation that comes from observations.
Formula?
Not formula. Not formula. It's again. See, okay, you guys have to be, you guys have to be more on top of it if you want to be competitive.
Empirical equation?
Empirical equation. That should come quick because I talked about an empirical equation how many days ago? Yeah, your first day. By now, the first day stuff should be like kindergarten stuff, right? That's usually the way it's supposed to work. By the time you hit the final exam, the first day stuff is like the kindergarten stuff because you've seen it so many times. It becomes so easy. That's the way you want to do your study. Okay? And so empirical equation, wow, that took a long time. I know there are people in this class who want to go to medical school. You have to really think about, Okay, let's go on to next. So this table is a little weird to use, so just be aware of that. And please do not write a density of water at 415 grams per milliliter. that would just show that you're totally clueless about the density. Obviously, this is a beginning class, so I'm not going to take it like that. But you know, if you were out in working in science, people would automatically
Laugh.
write you off. What's that?
Just laugh at you.
As potentially dangerous. Okay, because it's not, you know, we can't know everything, obviously. There are many things that are going to be not known. So, for example, I don't know the kilogram, and I don't really care how the kilogram's defined, but, you know, there's certain things, like if you're working on certain things, then you need to know. So anyway, the kilogram, you know, I forgot. This is what I was thinking, France. I was looking for the image, but the image is actually, where's the image? This is the image. This is from our PowerPoint here. So how is the kilogram defined? The kilogram is not defined by having 1,000 grams. It's not defined by having ultra pure water. Ultra pure water is not so easy to get. I used to, at UCLA, I used to use ultra pure water. It was very expensive. It was located in the psychology building. So once a week, I'd wheel my cart out to the psychology building and get 5 gallons of ultra pure water. It was located, I think, in the basement of the psychology building. And what it was a still. There was one distillation still. Well, actually, there's more than that. First, we had, what did we have? We had ion exchange, so we got DI. And then we had reverse osmosis, and then we had distillation, followed by another distillation, followed by UV. And even at that, you know, I couldn't store them in glass because glass would leach out. I had to use polyethylene. There was much less stuff leached out from polyethylene than from glass. And so you use polyethylene, especially when it comes to ions. You know, it depends on what type of glass you use. If you use quartz glass is very pure, you know, just SiO2. It's a compound. But most glasses are a mixture, or somewhat of a mixture, because of the amount of ions you can put in the glass. Ions are like sodium ions, you know, electrolytes, that type of stuff. It's variable. They, you know, otherwise they have a pure sample of water here or something and say that, okay, there's 1,000 grams of water here. But it, you know, this cylinder, I mean, this mass is defined. A kilogram is defined as the mass of this, which is stored in a vault in France. That's so inconvenient. It's so inconvenient because the only way you can tell if you have exactly a kilogram is by this mass. This mass is defined as exactly 1 kilogram. You know? Well, a kilogram weighs 2.2 pounds. Well, I got a scale. The scale weighs 2.2 pounds. Is that exact? No, it's actually, this is just rounded to 2 sig figs. It's 2.202 pounds. I mean, it goes on like pi, you know. How many digits do you know pi to?
Not that many anymore.
I know it to 3.14, but I met this person who knows it to 50, and I thought, why do you know it to 50? And so I asked him, well, that's my passcode. Well, that's a secret, so I don't want to give away the passcode. So it's between 0 and 100 digits, they know it. Maybe it's not the best passcode. But anyway, going back to this, the meter is a lot easier to define because the meter is the length of travel by light in a vacuum. Although it's hard to get a perfect vacuum, people are working with this. The vacuum is not easy, and even with the most expensive vacuum apparatus, it's still not a perfect vacuum. Nobody's achieved a perfect vacuum. People have achieved close. And so this is ultra high vacuum, UHV. UHV apparatus. I think. Let's see if it comes up. did it correct. This is what it looks like to try to get high vacuum. You have to use this stuff that looks like submarine, because when you suck out the air here, there's still 15 pounds of air pushing for every square inch on the outside. And so if it isn't strong like this, then it can collapse and implode like a submarine would. That is when you suck the air out of there. And not only that, they want to do experiments. There's windows here. These windows are thick, like submarine glass windows, and still there are leaks because they have all these joints. It makes vacuum leaks terribly difficult to deal with. And so things tend, even the joints present the biggest problem, but things like helium can leak through the stainless steel. This is very thick-walled stainless steel, like 3/4 inch thick. You can get vacuum leaks that way. So you bake it out. So working with vacuum is always you spend a lot of your time trying to figure out what the leaks are and getting rid of the leaks. So it's quite a challenge. But if you want clean stuff, this is the way you do it because there's no contaminants to it. And so some guys had a brilliant idea. I went to see a talk once, because this ultra high vacuum, you can get a much better vacuum in space. And so these guys had a brilliant idea. They wanted to grow the purest crystals possible of silicon, or maybe it was germanium. And so they wanted ultra pure crystals because one piece of dust gets in there. One piece of dust is huge compared to atoms, right? One piece of dust gets in there, it destroys it because the circuits are getting smaller and smaller. And so they have these clean rooms where they filter out as many of the particles as possible and contaminants. But if you can do this in a vacuum, then you suck out all the contaminants and potential filth. And so what they did was they designed an apparatus to synthesize and grow crystals out in space. And so they had some kind of arm that attached to the space shuttle, and this arm would deploy out, and then they'd have their apparatus and they'd just grow them in the vacuum of space. But it turned out when they got the samples back to Earth, they were much more contaminated than the ones they could grow in a clean room in a lab here. Do you know why? Because the space shuttle has these things called aerogel tiles. Aerogel tiles are like lighter than air. They're amazing. And they're insulator tiles, and they feel lighter than air, and I think they are less dense than air, basically. They're aerogel tiles. They have huge surface area. Well, when they went out in space, the surface adsorption, where gas molecules get stuck on the surface, and so when they're out in space, everything degassed off the tiles off the space shuttle, heavily contaminated the crystals. So it was a great idea, but it didn't work in practice. That was an interesting talk. That was an interesting talk about semiconductor manufacture, and there are other problems though with semiconductor manufacture that. So it goes on to show, that sometimes, having good general basic knowledge helps because at this talk, one of the guys, was working one of the chip manufacturing plants here in the Silicon Valley, and he was talking about, the defect rate, how many chips they had to throw away because of defects. And they got the cleanest room possible, the absolute cleanest room possible, and they still could not get rid. They got the room cleaner and cleaner and cleaner and cleaner, yet the defect rate stayed the same. And so why is it that the room gets cleaner and the defect rate stays the same? The defect rate should be going along with the cleanliness of the room, right? It turns out that, the engineer in charge of this was, this is what he said. He was at some kind of space talk, and space is not his thing, but he was at this space talk, and they were talking about cosmic radiation. And then he thought, then he made the connection, could the defects that they're seeing be due to the cosmic radiation that's bombarding the Earth continuously? And so what he decided to try was to shield the manufacturing plant from cosmic radiation. And it turned out that was it. The defects were due to cosmic radiation, so they ended up shielding the room and cleaning the room. But he said he would have never thought of that unless he, broadened his horizons. There's a lot of people say, "I'll never use this." I hear that all the time. "I'll never use this. Why do I have to study this?" You never know, what kinds of connections you make as far as, and you never know where you end up. My lab mate who is doing. He was doing some spectroscopy work like this kind of stuff, with lasers and whatnot, and computer modeling. He ended up he ended up working at HP, doing data, big data, and so nothing related at all to chemistry. So you never know where you end up. But he had good broad knowledge on a lot of stuff. But he got a PhD. He didn't think of it as a waste at all. That's what got him to the big data thing. Well, anyway, go on. Other than that, for definitions, for example, how is the Fahrenheit defined? I know how Celsius is defined. Celsius is defined as 0 degrees Celsius is freezing point of water. 100 degrees Celsius is, that's easy. Kelvin scale. 0 Kelvin is absolute zero. What happens at absolute zero? Yeah, motion stops. What is 0 degrees Fahrenheit? I'm sorry?
Is Fahrenheit based on body?
No, it's not based on bonding.
Body?
Yeah. I thought that. I thought that there's a scientist, Lord Fahrenheit, goes outside. Boy, it's cold. This is probably the coldest day I've experienced, so calls that 0 degrees Fahrenheit. Maybe it didn't get that cold where he lived. That's what I thought originally, but I was wrong. It was just my imagination. Do you know how it was defined? It was defined, that was the freezing point for salt water. A certain, and it's repeatable because it was a certain salt that, only a certain amount would dissolve before it became saturated, so you could consistently repeat that temperature each time. It's like 4 degrees. We always think about how reproducible is it. And so, for example, 4 degrees Celsius, if you tried to do that in the lab, it's not very reproducible. One day it's a little warmer, one day it's a little colder, that kind of stuff. But the freezing point of water is easily reproducible. It's 0 degrees C. You can have an ice water bath that's 0 degrees C. And so you can do a salt water bath, which is colder. Salt water freezes at lower temperature. How is a dozen? Who came up with a dozen? 12 units. What? I don't know. Why isn't it 10? Because our counting system's by tens. Why isn't the dozen 10? Why is a dozen 12? And so my imagination, I never bothered looking up because it's not that important, but I figured maybe it's the oven. The oven fits a dozen loaves, maybe?
Why is it 13 in a baker's dozen?
I don't know. But there are certain things you need to know, though. And so the ones that you need to know are important to know.
How did the Fahrenheit boiling point, how was that?
Well, the Fahrenheit boiling point, it's kind of tricky because do you know that water freezes at about 32 Fahrenheit or exactly 32 Fahrenheit? Water freezes exactly 32 Fahrenheit, and water boils exactly 212 Fahrenheit. So what I assume is that 0 Fahrenheit was set here, and then they decided to set the freezing point and the boiling point. They could make the degree Fahrenheit any size they want. And so they say, okay, we want to do this. Let me tell you, I got a car. I got a car that has the temperature in Celsius, you know, and then they just switched it over to Fahrenheit. And so a car that jumps from 22 to 23 Celsius. So let's say one temperature is 22, the next temperature is 23. That's too big of a jump for me. I can't stand it. Can't stand it because I'm used to Fahrenheit. When you do Fahrenheit, Fahrenheit is like a half a degree Celsius. And so I can fine tune the temperature more, right? And so basically I assume that they just pick the degree. The degree Fahrenheit is like this, the degree Celsius is like this. It's a bigger jump. In fact, it's 1.8. A degree Celsius jump is 1.8 times bigger than a degree Fahrenheit jump. But anyway, so they're at Liberty. Actually, he kept very detailed notes. It's probably all written in the notes how all that stuff is figured out. But it's not so critical. There are going to be things that you need to know how the definition. One of the things that you absolutely must know how it's defined is something called the mole. The mole is a very strange number. It's called Avogadro's number, and you absolutely, positively need to understand where that number came from and how it was defined. Okay. But the kilogram, we can live without that. Here, how many grams are in 0.711 kilograms? 711. That, to me is pretty basic. 711. Convert milligrams to kilograms. This I don't do it in one step. I do it in several steps. So let me show what I would do here, based on things that we should know. So if I have 5.25 times 10 to the 5th milligrams, mg, then I need to get rid of milligrams. And so going to milligrams, I can go milligrams to grams. There are two ways I can write this. The usual way is I just say there are 1,000 milli-units per unit. So 1,000 milligrams per gram. That's the normal way to do it. I don't do it 1 times 10 to the minus 3 grams. The definition of milli is 1 times 10 to the minus 3. So I'll do it this way. And then I need to get rid of grams. So we know that there's 1,000 grams per kilogram. So let me ask you this. Okay, how many sig figs here? 3 significant figures. How many sig figs here in 1,000? 1? 1 according to the rules, but you got to know that this is not a normal 1,000. This is by, it's exact. This is by definition. There are infinite number of sig figs in 1,000. Infinite. There's exactly, it's not approximately 1,000, it's exactly 1,000 milligrams. This is where you need to know how things are defined, because this is how you can tell. How about in 1? How many sig figs in 1? Most people say 1, but that's wrong. There are infinite. And the same thing here. How many sig figs in 1,000? How many sig figs in 1? Infinite. So this is why you need to know certain definitions. These ones are going to be important. And so how many kilograms is this? Well, we could do this, we could try to do this on our head. This would be 10 to the third, 10 to the third, so it's 10 to the sixth, 10 to the minus 6, so it would be plus 5, would be 10 to the minus 1. So 5.25 times 10 to the minus 1 kilograms. Or, this one is better written in decimal form, 0.525. Let's see if I got it right. 0.525. Okay, a fruit drink is sold in bottles that contain 1,892 milliliters. Express the volume in cubic centimeters and in liters. Well, one thing you need to know is this. 1 milliliter is defined as 1 cubic centimeter. The same thing. And so a cubic centimeter and milliliter are used interchangeably by chemists because they just, either way, it's your preference. I prefer milliliters because it's easier to say than cubic centimeters. But this is just my personal preference. And so 1,892 milliliters is the same thing as 1,892 cubic centimeters. Same thing. Or we could use dimensional analysis to do the conversion, but no. 1 milliliter and 1 cubic centimeter are the same volume. Okay, now we're going to go to liters. And so, 1,892 cubic centimeters, there's going to be 1,000 cubic centimeters in 1 liter, or 1,000 milliliters in a liter. And so they were dividing by 10 to the third, so we're going to multiply by 10 to the minus 3, and so this is going to be 1.892 liters. I just moved the decimal 3 places over, 1.892 liters. Okay, then we check it, it makes sense. All right, now let's talk about the rules for sig figs. Sig figs, we can only have one uncertain digit, it's the last digit. The last digit is the one that contains that wiggle room, the last digit. And therefore, we're restricted to the number of digits we can record. And this is just standard practice in science. The last digit's always a little bit uncertain, it's not exact. And so the thing is this. If I look at this, is this bigger than 1,800 centimeters? Is this length longer than 1,800 centimeters? Absolutely true or sometimes false? Is this going to be longer than 1,800?
Yes.
Yes. There's no uncertainty in 1,800. Is it going to be longer than 1,890?
Yes.
Absolutely. Is it going to be exactly 1,892?
Yes.
No. No, because normally all measurements, whenever you take a measurement, can you measure things exactly? Like, for example, I want to measure the density of water exactly. I know at 4 degrees C, maybe it's exactly 1. Is that something that's easy to measure? No, all measurements are going to contain uncertainty. And so all measurements contain uncertainty. So this is 4 sig figs, if it's a measurement, which I tend to think it's a measurement, versus if I said, well, it depends. It depends on certain things. Like, so for example, if you had a 50,000 gallon swimming pool, how much chlorine do you need for a 50,000 gallon swimming pool? Well, in that case, you go, oh, 50,000 gallons. 50,000 gallons is only 1 sig fig, but you go, but you don't, you just want it as a reference point. If you want it as a reference point, then you say, well, about how many, whatever chlorine, about how much chlorine do I need for exactly 50,000 gallons? So here's where you might define it as being exact, rather than 1 sig fig. Because otherwise it would be anywhere between 45,000 and 54,000. Well, uncertainty in measurement, this is all a measure of what we call precision. So if this is a meter stick right here, how long is this board? I would say this board looks to be about 0.685 meters. Would you agree? Would you agree, 0.685 meters? In fact, I think I'm better than that. I'd probably say it's going to be maybe 0.6851300 meters. Would you agree with that? No, because I'm being overly precise. I'm saying for certain it's 0.6, for certain it's 0.68, for certain it's I'm just saying that the uncertainty is in that last digit, the 0. That's being overly precise. this doesn't have that much precision. And so this is, we can only guess it's between 0.6 or 0.7. It's around 0.6 or 0.7 meters. That's only one sig fig, so, you know, there's a big spread of uncertainty, yeah.
So you don't want to be overly precise?
You can't be. In science, you're not allowed to be overly precise. It depends on the, that's why here, that's why they're saying 0.7. Normally we go half this, so normally it's 0.7 plus or minus 0.05 because we're better at eyeballing things, right? And so this is called maximum error here, and usually for maximum error, this is not being very generous with their maximum error. Because they're saying it's between 0.6 and 0.8. I don't think it's 0.8. I don't think it's it could be 0.6. I think it's closer to 0.7. And so it depends on what your confidence is. What's standard in science is to take half that's smallest. And so this is overestimating it. We'd usually go 0.05. And that's what I've been doing. I've been taking half the smallest. All right, this is a more precise meter stick. The previous meter stick wasn't very precise. When you look at this meter stick is much more precise. And yeah, you can see I was way off. I was calling 0.68. This is closer to 0.63, looks like, doesn't it? And this looks like about 63 centimeters, doesn't it? Could I say 63.5 centimeters? Or would that be pushing it? That's pushing it. This is going to be, you know, they're saying 64. The reason I did, it may, yeah, 64, because if I cut it in half, it's closer to 4. 64, I was off. Looks closer to 64. Now, this is even more precise. You see, the higher the precision, the more sig figs we can get. And so this is much better because, yes, I see for sure it's 64. There's no doubt it's 64, right? But it's a little bit above, so it's 64 point, and here we guess. We're going to guess 64.2. That sounds good. So 64.2. The last digit is always the guess digit or the estimated digit. And so we're only allowed one guess. We cannot have multiple guesses. And so this is 64.2. So that's the difference. Now look at this one. This is much more precise. And so what we're doing is we're going from low precision to high precision. High precision means that the range of uncertainty is very tight, very small. And so for sure this is 64.2, but you know what? It looks between 64.1 and 64.2. Can you see that? And so we don't have to guess. We don't have to guess. When I read this, I see, without guessing, it's 64.1 and just below 64.2. So I'd say this is 64.19 or 18. That's my guess. I'm only allowed one guesstimated digit. And so I'm looking at 64.18 or 19. What are they looking at? They're looking at 64.3. 64.3, this is totally wrong. Do you see this is totally wrong?
Yes.
Yeah. For one, they're guessing 3. We don't have to guess. If we go 64.3, it didn't even reach 64.3. There's no guessing there. It's the next digit. This is totally wrong. 64.18 should have 4 sig figs, higher precision. Okay. There's two types of uncertainty that we have in measurement. One type of uncertainty is how tight, how precise we can be, right? We want higher precision.
Yeah.
The other thing is this. It's even though we're using a very precise meter stick, are we getting an accurate answer? You know what? Precision is tight. Accuracy is the correct answer. And so somebody could be using a high precision tool like this, but screwing up the measurement. How could they screw up the measurement? Well, we don't know how it's lined up on the left side. Is it lined up or is it off a little bit? You know, if it's off a little bit, it could be reading too long or too short. And so accuracy depends on the user, if they're using the equipment correctly, whereas precision doesn't. Precision just means, you know, how many sig figs you can get. And accuracy depends on if the instrument's calibrated. Because this is a piece of wood. Wood, do you think it shrinks? Or maybe expands? Have you? I don't know if you've been in an old house. As the humidity level changes, sometimes it's harder to open the doors and close the doors. Have you ever experienced that? Well, nowadays doors are made out of different materials, but if you have a solid door, sometimes that happens where, you know, it expands or contracts a little bit with humidity. These have been dried, so they shouldn't expand and contract too much, but, you know, could be off. We don't know. Also, these are mass-produced. Thermometers are mass-produced. Our thermometers, you put two of our thermometers in the same cup of water, they give two different readings. Why? Because they're mass-produced. They're cheap. They aren't high-precision, high-accuracy instruments. If you want high-precision, high-accuracy, you better pay some money. Make sure that those are reading correctly. And you guys will see that the thermometers are. And so what we do is we calibrate it first to make sure it's reading accurately, and then we take a measurement. We always do calibration. Except tomorrow's lab, we aren't going to do calibration because calibration is the job for the technicians here. But when you're working in science, then you're responsible for making sure everything's calibrated correctly. How many sig figs? 3. How many sig figs? Okay. All right, rounding. You know, if we need to drop a digit, these are the rounding rules. If it's less than 5, don't just drop the digit, don't change anything. If it's 5 or greater, we increase it by 1. And so it depends. If we round this 2, do we change the 5? No. If we drop the 5, do we change the 7?
Yes.
Yeah, we change it to 8. If we drop the 7, this would go to
33.
If we drop this 2, it'd go to 4. Now, what if we did this? What if we said, okay, I see the 5 here, so the 5 rounds this to 8, which rounds this to 3, which rounds this to 5. So then that would round this to 2. Can we do the domino effect? No, domino effect is not allowed. We can't do successive. We're only allowed 1 rounding per calculation. Since we're only allowed 1 rounding per calculation, and our book is guilty of this, and same with the Chem 1A book, we have to carry extra digits. Let's say I'm only allowed 2 significant figures according to the rules, but I'm not at the final step, I'm in an intermediate step. I carry extra digit here. I carry an extra digit to avoid round-off error. A round-off error is a problem. Let's say you're supposed to earn 1. Let's say you're supposed to earn interest on your savings account, and the interest is you're supposed to earn 1.04 cents per day. You're supposed to earn 1.04 cents per day. And so you have your money in the bank for 1 year. Do you want your bank to do intermediate round off? Every day they're going to round it to 1.0 cents. 1.0 cents. Or actually, whatever. Let's make 1.4 cents. And so they'll round it. You're supposed to earn 1.4 cents per day, and they just, every day they do this. By the end of the year, you're going to be short. Quite a lot. Obviously, the bank would not give this because then, and then round it per day because then they'd lose money, right? And they'd figure out a way to not lose money. And so we do the same thing in science because each time you do these round-off, intermediate round-off steps, you know, each time you round, it introduces something called round-off error. And so by the end of the calculation, if you have a multi-step calculation, you're way off. And so only 1 rounding step per calculation at the very end. All right, now there are rules here. Actually, let's stop. We'll take a break. There are rules for addition and subtraction and rules for multiplication and division. Let me just show you addition and subtraction. When we're doing addition and subtraction, this 5 contains uncertainty, right? This 4 doesn't, the 0 does here. The last digit's the one that contains uncertainty. And so if I take this 5, which contains uncertainty, it's going to make all the 10th digits uncertain. And so this 8 is going to be uncertain.
So you want uncertain.
I'm sorry?
You want uncertain.
No, we're only allowed one uncertain digit. For sure, this is uncertain, this is uncertain, this is uncertain, this is uncertain, this is certain. Because this one doesn't contain any uncertainty. And so, for addition and subtraction, we don't care about how many sig figs there are, we care about how many decimal places there are for addition and subtraction, because we got to carry the uncertainty down. And so if the uncertainty shows up here in the 10th, then we got to carry it down here. And that means all these digits aren't allowed. Uh-huh.
If that 3 instead was a 7, would you round it?
Yeah. If this were a 7, I'd round up to 9. That's addition and subtraction. For multiplication and division, we just care about the number of sig figs. And so let's take a look here. For multiplication and division, how many sig figs here? 3. Here?
4.
Here?
4.
4. 4 sig figs. Zeros after the decimal are significant as long as there's after a non-zero. So this is actually 4 sig figs. This is very precise for 1 liter. And so if there are 3 sig, we're only allowed 3 sig figs here. So how do I express this in 3 sig figs? 0.0823. That would be 3 sig figs. Let me just finish with this and we'll take a break. 0.0823. But what I want you to show on the test is I need to see what digit you drop. And so you got to carry 1 extra digit at least, and show me how you rounded it. And so a lot of people, what they do is they leave this in the calculator and just write this down. I need you to write down both so I can see both. Just don't leave it in the calculator. All right, let's take a break for 10 minutes and then we'll start again.